Okay, section 4.2, the shape of a graph. In section 4.4, we discussed how the sign of the first and second derivatives affect the extreme values of function f. Then, all those informations, all the basic concept of calculus that we have covered so far can be used in determining the shape of a graph that include y and x intercept and symmetry and continuity and domain and range and infinite limit on the x-axis and y-axis as x goes to infinity and y goes to infinity, and vertical and horizontal asymptote, absolute maximum and minimum, and local maximum and minimum, and critical numbers and increasing and decreasing part of functions. And also concavity and oblique asymptotes and inflection points can be used to determine the shape of the graph. Okay? So from here, if the slope changes, if slope increases, then if f prime increases, then we can easily see the graph have a concave downward like this. Okay, and if f prime decrease like this, then we can see we can have a concave upward. Okay, here this figure says if f prime increase, f primes are increasing like this, it's getting steeper, then we have concave downward like this, concave downward. So as you see, it's like this downward. And if f prime decreasing, it's getting more negatives like this, then we have a concave upward like this. Okay, and concavity test says if double prime is of x is positive for all x in I in the interval, then the graph is concave upward, like what you saw in the example, the figure 1a. And f double prime of x is negative for all x, then the graph of is concave downward like this. And that's the concavity test, and determine the open interval on which the graph of f of x is equal to cube root of x is concave upward and concave downward. So you can use the concavity test, but also you can draw the graph to check it out where it is concave downward and concave upward. Here the figure 2 says it is concave downward from the 0 to infinity, and concave upward from minus infinity to 0. Here those are the example of inflection point where f double prime of the f prime of x changes. F double prime of x is equal to 0. And oblique asymptote. These are the. Okay, here I will show how this. Let's see. The example 2 is so oblique asymptote. The equation of oblique asymptote or slant slope is the kind of asymptote line which shows the limit of the curves when x and or y approaches to the infinity or negative infinities. Here is the example that shows the oblique asymptote. Okay, let's see some examples of oblique asymptote. We make a copy of this command that shows the graph of this function and the asymptotic, one of the oblique asymptotic lines. Let's put here. Then let's see the graph. Here, this P1 shows the graph of x plus 2 plus 1 over x, and as you see, as x goes to infinity, this value approaches to a certain line, which is this, is x plus 2. So you can easily see this x plus 2 works like a asymptotic line that we have seen it. Okay, and for the other examples like this, here, for e to the x times y minus x equal to 1, then in this case y is equal to x works as the oblique asymptote in it. Let's see. Here, let's draw the graph. Then, as you see here, this is the exponential function and of this graph. This graph, x plus e to the x minus x, then this y is equal to x shows where this given function converges. And so this is a asymptotic line. So you can easily distinguish it. If we have this function, then if you can write it, then if this goes to this approach, you know, e to the minus x, the shape of the graph of e to the minus x, then you can easily find the asymptotic, oblique asymptotic line from the function that include those known graph. Okay. Okay, then with those informations, now let's see how we draw the sketch of the graph. This is the method. Find the domain and range first, find the x-y intercept symmetries and vertical, horizontal, oblique asymptote, and compute the x prime, f double prime to find the critical numbers and inflection point and extreme values and intervals for increasing and decreasing and intervals for concave upward and downward. Then use all those given the information that we have found to draw the sketch, the shape of the graph. Okay, that's the way. This is the table that you're supposed to make to draw it. But actually, I can draw it easily. I can easily draw the graph by just typing x square minus 1 over x cube in here. Let me see. Let me show you. Here, plot what? Then x to the what? Square? X cube minus what? X square minus 1 over x cube. Okay? X square minus 2, 1 over x cube, like this. I think I need one more. I think here we need this. Okay, here. I think that will do it. Okay, here I can plot. Okay, here. I can easily draw the graph of it. I can, without it. I can give a maximum or minimum. Control V, and Control G, maximum, Y maximum, for example, 10, and Y maximum 14, X maximum, Y maximum, Y minimum, X maximum, something like that. Let's draw the graph of it. Let's here 10 minus 10. Anyway, we can draw the graph of it. So to draw the this graph with those. Similarly, we can draw the graph of the function to the sketch by fixing out all the collecting all the given all the informations to draw it, and also we can draw the graph directly with the computer algebra system of your choice. So we can draw the graph of those to find the sketch of it. This is the graph of the first. This is the graph of the first derivative of a given function. This is the graph of the second derivative of a given function from -2 to 5, and this is the original function f. So this is a blue. So as you see, the blue function is the original function. The second derivative, first derivative, and second derivative shows they are all in one graph. Okay, these things can be found in with the method that we have learned, but also now we have other tools like this. Okay, here, suppose we have this graph, this curve, then we can draw the graph to find the local maximum and minimum, or we draw the graph first to find it, or we found all the information to draw the graph. That's your choice to do it. Okay, and these examples shows it. I think yeah, you have the solution, so you may try to draw the graph and then find the local maximum and minimum and intervals of increase and intervals of decrease and inflection points, etc. Yes. So you can upload some of the problems of your choice of solving the different problem with a similar problem, which is a little different than the given one, of your choice of complexity, or you solve the problem with the computational computer algebra system of your choice to get the answers on those problems. Okay, here you may do the I recommend you to use Chrome or Firefox to do the computation of it. So this shows the vertical asymptote and local minimum, and where is the increasing interval and where is the interval of decreasing, and it shows everything what you need. The vertical asymptote at -π/2 and π/2, etc. So you just go through it and try to solve at least 3 problems per week, and to look over other solutions and revise and finalize those before your submission day of homeworks. I think that covers the section 4.2. Is there any questions?